In this lecture, I'd like to talk about a general method for solving systems of linear equations. And these systems of linear equations could have any number of equations and any number of variables. And the method is called Gaussian elimination. And we actually already saw the idea last lecture, so I just like to recall that. This was one of the systems of equations we considered in the previous lecture. And it corresponds to, so this corresponds to the augmented matrix So what did we do to form the augmented matrix? We just took each equation and we ignored the x1, x2, x3. We decided those aren't so important for the process of actually solving it. What we really want to keep track of is the coefficients. So we have 2x1 plus 0x2 plus minus 3x3, and that equals negative 2. And then similarly, we have 3, 1, negative 2, 5, 2, 2, 1, 4. Okay. And any system of equations we start with, we can write in a corresponding augmented matrix. Okay. Let's try to formalize the process that we did last time oh, why did I put a 2 there? I'm not sure. That should be a 1, right? Okay. Right, so I want to formalize the process that we did last time in order to solve this equation. And the way to make this formal is to introduce the so-called elementary row operations. Okay, elementary row operations. So these are things I'm just going to do to the rows in this matrix. And I'm not even going to think so much about the equations. I'm just going to think about manipulating rows in this matrix toward a goal of getting the matrix in a certain form where it'll be easy to write down the solutions. So here's what I'm allowed to do. First, I can multiply any entire row. Right? So multiply any row by a constant. I don't want to multiply by 0 though, so let's say non-zero constant. Well, why am I worried about 0 so much? I don't want to change the solution to the system of equations. So if I multiply a row by 0, that sort of kills off all the information that that row is giving me. If I multiply by another number, I maintain the same solution to the system of equations. So I'm allowed to multiply any row by a non-zero constant. The second row operation, I can add or subtract a multiple of any row from any other row. So any row from any other row. Okay. So for example, I can take the third row and replace it with the old third row minus 2 times the first row if I wanted. Okay, and then the third elementary row operation is I can just swap any 2 rows that I want. Okay. So none of these actually change the solution to this this system of equations, but I can use these to get me closer to my goal, which is, here's my goal. My goal is a matrix that looks like this. Okay. Any number there, but I want zeros below it. Okay. So here's my first equation. And then I'll have any number here, but zeros below it. And my third equation, and then my third equation will look like this. So these are just any number. And we're not always going to be able to achieve this exact goal. We'll talk about that later, but This is what I'm trying to get. Why am I trying to get this form? Because think about what this third row is saying. It's just saying x3 equals, or this number times x3 equals this number. That tells me what x3 is pretty much right off the bat. Then I can use this information to go up one row, figure out x2, go up another row, figure out x1. Okay, let's, and a process of applying these operations in order to get to this goal is called Gaussian elimination. So let's do it in our example. So I'm going to start with our matrix 2, 2, 1, 4. What do we want to do first? We want to turn that 3 into a 0. In fact, while we're at it, let's turn that 2 into a 0 also. So same what we did last time, but this time I'm going to write it down in terms of elementary row operations. So let's say this is a row 1, row 2, row 3. What exactly am I going to do here? I'm going to take my old row 2 and I'm going to replace it with, I'm going to take my old row 2 and subtract an appropriate multiple of the first row. What multiple do I want to choose? I want to choose 3 times the first row because I want to turn that 3 into a 0. Okay, so this is saying I'm doing the second row minus 3 times the first row, and then I'm putting that in for the second row. Okay, so I'm replacing this with this. Okay, that's what I mean by this arrow. It's like replace this with that. Okay. So well, we're not doing anything to the first row. Let's just leave that as is. Okay. Now I'm going to subtract 3 times the first row from the second row. So I get 0. So 1 is just going to stay a 1. I have 2 minus negative 3 times 2, or negative 3 times 3, sorry. So that's 2, negative 2, plus 9, which is 7. And I have, this one's going to become an 11. And while we're at it, let's replace the third row as well. What do I want to replace the third row with? I want to take the old third row, but I want to subtract off an appropriate multiple of the first row in order to get rid of that 2, in order to make that 2 a 0. So I want to subtract off 2 times the first row. And we did this last time, so I'll just write it out quickly. 0, 2, 7, and this becomes an 8. Okay. What next? Our goal. That 2 is the only thing standing in the way of our goal, right? So, what do we do next? Well, the first row looks good, right? The second row looks good. I want to take the third row and replace it with, so here's R3. I'm going to replace it with you see how if I subtract off a multiple of the first row, it's not going to help me because that's going to change this 0 as well. So I need to just use the second row. So I'm going to replace it with the old third row minus 2 times the second row. Why 2 times the second row? Because I need something that will turn that 2 into a 0. Okay, so 2 minus 2 is 0. 7 minus 14 is negative 7. And 8 minus 22 is 14, negative 14. Okay, that's a 0. All right, let me put in these red dividing lines too, just to separate the coefficient part from the this side of the equations. Yeah, this is great. So this is our goal here, right? And what we could do is we could say, well, what does this correspond to? This corresponds to, this third row corresponds to negative 7, x3 equals negative 14, so x3 is 2, and then etc. We could go up and say, well, what does this row correspond to? x2 plus 7x3 equals 11, but x3 is 2, so we could figure out what x2 is. But the cool thing is we can actually keep going with the matrix. And this is actually really satisfying because you're going to see the solution you can just see the solution by looking at the matrix. You don't even have to convert it back to these equations. Let's take the third row and turn that -7 into a 1. Okay. How do I turn the -7 into a 1? I don't want to add a multiple of either of these rows, right? Because that will maybe introduce some numbers back here that I don't want. Instead, I can just use, I don't think we did our first one yet, right? So I can multiply a row by any non-zero constant. I'm going to multiply this last row by, so R3 I'm going to replace with -1/7 times R3, right? So this will become a 2. Okay, can we keep going? Yes. 1, 0, 0. Okay, here's what I want to do next. I want to try to turn all of these into zeros, except for the diagonal entries. So I'm going to try to turn that 7 into a 0. How can I do that? Well, I could find an appropriate multiple of the first row, but that will turn this 0 back into something non-zero. I don't want to do that. I've made progress here. So instead, I'm going to look down to my third row, and I see there's a 1 there, and there's a 0 here. So if I add a multiple of the third row to the second row, I will not affect these spots here. Do you see that? So I'm going to take my old second row, and I'm going to add, or I guess I'm going to subtract. So I'm going to do R2 minus 7 times the third row. Okay. And what does that become? So the first row stays the same. This 1 is unaffected, right? The third row stays the same. But that 7 is going to become a 0. And what's that 11 going to become? Well, it's 11 minus 14, so a -3. That was pretty cool. We turned that into a 0. So can we turn that -3 into a 0? Think about how we would do that. While I'm writing out the matrix. Well, let's use this last row again, right? Okay, because that has zeros here and here. Those are not going to affect this part. So I'm going to replace my row 1 with the old row 1. How do I get rid of that -3? I need to turn this into a 3 and then add it, right? So I'm going to do R1 plus 3 times R3. 3 copies of R3. Okay, so again, this will be unaffected, right? Because I'm adding 3 times 0. That doesn't change it. That -3 is going to become a 0. And what's that -2 going to become? Well, I'm adding 3 copies of row 3. So I'm adding a 6 to that -2. So I'm going to get a 4. And we're done. So see what I mean? How you can just read off the solutions now? Because what is this saying? This is just saying x1 plus 0x2 plus 0x3 equals 4. x2 equals -3, right? And x3 equals 2. Okay. So we can just stay entirely in a matrix form and get the solutions. Okay. Just to kind of give a name for this part here is called, so you know, going from here to here to this triangular form is called Gaussian elimination. Going from here to here, all the way to the ones in the diagonal form is called Gauss-Jordan elimination. Just to distinguish it from Gaussian elimination. These are sort of fancy names, though, for a simple concept. And I looked this up in Wikipedia, and apparently So it's not Gauss who first discovered this. It was so it's apparently known to Chinese mathematicians about 2,000 years ago. But yeah, so these names have stuck: Gaussian elimination and Gauss-Jordan elimination. And this is what's known as the echelon form of the matrix, and this is actually called the reduced echelon form. I'm going to introduce those terms in just a second, though. Okay. Before I do, though, I would like to show you how to tell a system of equations has no solution. So here's an example of an inconsistent system. Remember, inconsistent means no solution. Okay? And consistent means at least one solution. Okay. Here's our inconsistent system. So negative 3y plus 6z equals 2. X plus 4z equals 1. And 2x plus y plus 6z is going to equal 0. Okay, let's try to solve this system, and we're going to run into trouble because it's inconsistent. But the first step is to put it in matrix form. So we're going to write the augmented matrix for the system. 0, negative 3, 6, 2 is my first row, right, because I don't have any x. And then 1, 0, 4, 1 is my second row. And then 2, 1, 6, 0 is my third row. Okay. Well, I'd like this entry to actually be a 1, right, not a 0. I'm trying to get the ones below it to turn into 0. So let's actually start by just swapping the rows a bit. Let's move the second row to the top. So we'll say, what is this row operation? We're just swapping the rows. Right, that's one of our 3-row operations. I'll move the bottom row to the second position, and I'll move this one down. Okay. Well, what next? I'm sure you know what to do by now. We need to turn that 2 into a 0. How do we do that? We're going to replace the second row with the old second row minus 2 copies of the first row. Okay. Write the first row as is. And then I have 2 minus 2, which is 0. 1 minus 0 is 0. And, 1 minus 0 is 1. It's a mistake I like to make a lot for some reason. And then 6 minus 2 times 4, 6 minus 8 is negative 2. I also have to do this side, right? 0 minus 2 times 1, 0 minus 2 is negative 2. And the third row, so I would like to replace this position with a 0 if it were something else, but it's already a 0. So let's just copy down the third row. Okay. What's our next step? That 1 there is great, but I want to turn that into a 0 by using the previous row. So we're going to take row 3, and we're going to use a second row to cancel out that minus 3. So I'm going to take row 3 and add 3 copies of the second row. Right? Here's what we get. First 2 rows are unchanged, but the third row becomes, well, that 0 stays a 0. Okay, I'm adding 3 copies of the second row, so that becomes a 0. But wait a second. 6 plus negative 6, that also becomes a 0. Does this become a 0? 2 plus negative 6, right, is a 4. Negative 4. Okay, so there is my matrix. And I immediately see something out of the ordinary here, which is this third row. What is this third row saying? So this row says 0x plus 0y plus 0z equals 4, negative 4. Well, that's nonsense, right? Yes. No matter what x, y, and z are, this side is going to be 0. 0 doesn't equal negative 4. Okay. So I know how to tell if a system is inconsistent. I just do the row reduction. This whole process is known as row reduction, this Gaussian elimination. And if at any point I get something that looks like this, where so yeah, let's write this out. So if I ever obtain a row of the form bunch of zeros, 0, 0, maybe I have a lot of variables, 0, 0, 0. Okay, everything on the left side of the red bar is 0, but I have some non-zero number here. Where a is not equal to 0. Then, what can we say? Then automatically the system is inconsistent, right? Okay, great. So that's how we can tell. Okay, so next I would like to introduce what's known as echelon form. Just to motivate this a little bit, let's just recall, I think we had one other example last time that looked like this. Plus 5x3 minus x4 equals minus 30. And then we had x3 plus x4. This one actually turned out to have infinitely many solutions. Okay, let's write down the augmented matrix that this corresponds to. 2, negative 1, 5, negative 1, negative 30. And 0, 0, 1, 1, negative 6. Okay. We remarked last time that this was sort of the best that we could do, right? We couldn't use this first equation to sort of eliminate any variables in a second equation without reintroducing x1 and x2. And so we'd like to sort of have a general name for the form of a matrix where we've sort of reduced as many variables as we can, where we're sort of the closest to writing down the solution. And so one notion of that is called the echelon form of the matrix, or the row echelon form. So I'd like to define that. It's a really important definition. So a matrix is in row echelon form. Echelon essentially means a staircase. So row echelon form, staircase form, if the following are satisfied. So actually, let's start with this. So the first one is, let's say we have some rows that are all zeros. We want those to just be banished to the bottom of the matrix. So all 0 rows. We haven't seen that so far, but all 0 rows are at the bottom. And then that way we can say, in order to be in row echelon form, we need the leading entry of each row. And there's a name for the leading entry of each row. It's called the pivot. Okay, that's the leading entry of each row. So I'm going to circle those in this example. The leading non-zero entry, very important, because technically that would be the leading entry. So leading non-zero entry of each row is strictly to the right of the leading non-zero entry of the row above. Okay, so in other words, it's in this staircase form, right? So that 1 is strictly to the right of that 2. In fact, it's it's not even there. It's even further to the right, but that's fine, right? That's still echelon form. All of these matrices are in echelon form. So here are our pivots. I'm circling our pivots. Let's go back to the previous page we had. Okay, this is in echelon form. Here are our pivots. This is also in echelon form, right? Okay. Each time we go down a row, the leading entry is strictly to the right. The leading non-zero entry is strictly to the right of the leading non-zero entry above. Okay, so that's what echelon form is. Okay, is echelon form unique? That's a good question. So, given any matrix, can we find a unique echelon form? Well, no, of course not, right? Because look at this one. I could have just multiplied this row by something else, right? And turned that -4 into anything that I want. Right? So echelon form, row echelon form is not necessarily unique. But there is something that is unique called the reduced row echelon form. But before that, I just want to introduce a few more terms. So let's just draw a bigger example of row echelon form. Here's an example. Let's do a 4 by, well, let's see when I get bored. So these can mean any number, any non-zero. Or I guess these could all be 0, but this one here is non-zero. Okay. 0, 0. Let's say this one here is non-zero. These could be any number, literally any number. Say there's my pivot on this row. Okay, so I've circled my pivots. Then let's, just for fun, let's have a row of all zeros. Okay. So again, let's just say, these ones can be any number, okay? And this one is any non-zero number. This is an example of a matrix that's in row echelon form, okay? Okay, a couple more definitions. I said this course is going. A lot of this course is going to be learning the language of linear algebra, just because it makes more complicated concepts easier to talk about. Okay, for each of the columns of this matrix, I can think about it as being associated with a variable. Right? I can think about this one as being the x1 column. This is the x2 column, x3, x4, x5. So this number times x1 plus this number times x2, etc. equals, that number. Right? Okay. Some of these columns have a pivot, and some of them don't. Okay, so the columns or let's say the variables associated to the pivot columns, the columns with a pivot. In our example, that'll be 1, 3, and 4. Okay, associated pivot columns are called the leading variables. Leading variables. And the variables associated to the non-pivot columns are called free variables. Why are they called free variables? It's because we can essentially choose whatever value we want for them. So let's look back at this example. what are our leading variables and free variables? So x1 and x3 are our leading variables. And x2 and x4, so those are the ones associated to the non-pivot columns, are our free variables. And so it's saying we can essentially set x4 equal to anything we want, like we did last time. We said x4 equal to t. Well, then x3 is going to be -6 minus t. Okay, just using this equation. And then it turned out we could actually set x2 equal to anything we want also. Okay. And then x1 will be determined by that. So the cool thing about echelon form is we can immediately see how many free variables we're going to get. So in this example, we're going to have exactly 2 degrees of freedom to choose anything we want for the solution. Right? So x2 and x5 are free variables in this example. And then x1, x3, and x4 will be determined. Okay. Like we said, echelon form, not unique. I mean, let me actually put some numbers to these asterisks. Maybe I should have done that to begin with. So 1, -1, 4, let's do 2. We can make some of them 0 if we want even, right? And the next one, I have to start with zeros, and then this is going to be a non-zero entry. So let's say it's a 2. Let's put a 0 there. -4, 2. And this one, let's say, is a 1, 0, 5. Then we have a row of all zeros. Okay. Circle our pivots again. Okay. Echelon form is not unique. For example, I could have taken the second row and just multiplied it by a half, right? And then that would become a 1. So it's not unique. There is something that is unique, though. It's just called reduced echelon form. Okay, so one more definition. A matrix is in reduced echelon form reduced row echelon form. There's something called column echelon form as well, but this is row echelon form that we're dealing with. If, well, we have some extra conditions. So the first one has to be, it's in echelon form. So it's, if, first of all, it's in echelon form. It's in row echelon form. What's the second condition? Well, one thing we observed is that this 2 could have been a 1. We could have multiplied any row by anything we want. Let's fix all the pivots as 1s. So let's say all the pivots are 1s. Okay? All the pivots have to be 1s. And what else can we do? So there's one other thing that we can still do. Like even if this was a 1, we could take any multiple of this column or this row here, and then start changing the first row over here, right? We can add any multiple of this to this, and then these 3 numbers will change. So even if the pivots are all 1s, it's still not unique. But what if we specify that each pivot column has all zeros above the pivot? Okay, and it turns out it's pretty amazing. If you assert these 3 things, then the reduced row echelon form is unique. So any matrix you have, you can write down a unique reduced row echelon form. Okay. Have we seen any reduced row echelon forms so far? This is not reduced row echelon form. Why? Well, a couple of reasons, right? First of all, that 2 needs to be a 1. Well, that'll be easy enough to do. But that 5 has to be a 0, right? Each pivot column has all zeros above the pivot, right? So that 5 would have to be, we'd have to make that 5 into a 0. I think we've only seen one so far, which is actually this one here, this completely solved one, right? So we have 1s in all the pivots and then zeros above the pivot positions, right? So this is reduced row echelon form. Okay. For practice, let's take this matrix here and convert it into reduced row echelon form. Reduced row echelon form is useful for a variety of things. So I'm just going to copy down this huge matrix. If I somehow don't make a mistake while doing this, that'll be a miracle. Let's see, we have zeros. Okay. Okay, this is in echelon form, right? Here's a pivot, here's a pivot. It's the first non-zero entry on each column. And we have this stair step down. So each initial non-zero entry occurs strictly to the right of the leading non-zero entry of the row above. Right? So this 2 is strictly to the right of the 1. This one is strictly to the right of the 2. This one doesn't have any leading non-zero entry, but that's fine. Right? We said all 0 rows are at the bottom. Great. Okay, what should be our first step in turning this into reduced echelon form? First row I'm going to keep the same. Let's turn that 2 into a 1, right? Let's multiply the second row by 1/2. So 1, 0, -2, 1. This one looks good. 0, 5. And finally, all zeros. Okay, what next? Is it in reduced echelon form yet? First 2 look good, but this part is not good, right? Each pivot, here are the pivot columns. Each pivot column has to have all zeros above the pivot. So we need to change that into a 0. Let's do that next. Okay, this row looks good. This row looks good. Put all 0 down there. Okay. And then this first row is going to become 1, -1, 4, 0, 0, 10. What did I just do to the first row? What row operation did I do? See if you can write here what I just did. All right, so I took 2 times the third row and added it to the first row. So the first row became R1 plus 2 times the third row. Okay, we're almost there. One more thing to do. We need to turn that 4 into a 0, right? So let's go ahead and do that. I'm going to add, or I'm going to subtract, I guess, 4 copies of the second row from the first row. Okay. So I'll have 1, -1, 0, 0. And now this is going to become an 8, right? And this will become a 6. And am I done? Is this reduced row echelon form? I think it is. All right. So it's in row echelon form. All the pivots are 1s, and each pivot column has all zeros above the pivot. Right? 0, 0, 0. Notice we don't have zeros over here, right? But that's fine. So these columns correspond to, well, let's say that this is an augmented system. Okay. Because anytime I see a matrix like this, I think that this could represent some system of equations. So yeah, let's write out the system of equations. This would have been x1 minus x2 no x3, no x4, but then I have 8x5. This wasn't the original system, but this is what we're left with. And then I have x3 minus 2x5 equals 1. Right? You want to be able to go back and forth between the matrix and the corresponding system. And then x4 equals 5. Okay. What are my free variables and what are my leading variables? So my leading variables are x1, x3, and x4. My free variables, the ones that have a free choice, so my free variables are x2 and x5. I can choose any number I want for those. That's what the reduced echelon form is telling me. I can choose any number I want for those, and then I can express the other ones in terms of what I chose. So let's do that really quick. So these are the ones that I'm going to have to specify values for. So or specify parameters for. X4 is 5. Let's let x2 equal s and x5 equal t, let's say. Okay. I have a free choice. I can choose any number that I want. Well then, that x5 is t, that x5 is t, x2 is s. This is the beautiful thing about reduced echelon form. I'm basically just done, right? So like x1 is 6 plus s minus 8t. I don't even have any other variables that aren't free here, right? I just have the free variables. I don't have x3 and x4 in this equation, for example. And that's because I took the step of turning these into zeros to get it into reduced row echelon form. So here's x1. What's x2 going to be? S, right? x3, let's look at this equation, right? It's just 2t plus 1. x4 is 5. Don't get that 5 confused with an s. Maybe s is a bad choice. Try to make it look very curvy. That's an s, and this one's a 5. And then x5 is t. Right? So this is our parameterized solution. Okay. So 2 reasons why reduced row echelon form is so important. First of all, you can very quickly write down a parameterized solution. And the way you do it is by identifying your free variables. Okay, these are the columns without a pivot. And then you just set them equal to any parameters that you'd like. Okay. Then you just write out what the other equations are and you plug in those parameters. Okay. You write out the equations for the row, you plug in the parameters, and then you immediately have x1 expressed in terms of the parameters. You immediately have x3 expressed in terms of the parameters. And you can just write out your parameterized solution. That's one reason why it's useful. The other reason why it's useful is because of its uniqueness, because there's only one reduced echelon form. So you can sort of identify a bunch of different matrices with this one sort of canonical matrix. And that turns out to be useful. We'll see that later in the class. Great. So maybe to conclude this lecture, let's try to tie together a lot of the ideas we learned by doing a problem. So here's a problem that we should try. Okay, so I'm going to give you a system of equations, but it's going to have some numbers that have not been specified. So for what values of A and B does the system, okay, let me write out a system, x plus y plus 2z equals 4, and then the second equation will be 2x plus 3y equals A, okay, and then my third equation will be minus y plus 4z equals B. This is going to look like a very tough problem at first, but it's actually not. because we can use what we learned today. So for what values of a and b does this system have? You have to tell me all the values of a and b so that this has, first of all, one solution, or infinitely many solutions, or no solutions. Okay. Well, let's start by turning this into a augmented matrix, right? So the first equation is 1, 1, or the first row is 1, 1, 2, 4. And the second row is 2, 3, 0, A. And the third row is 0, minus 1, 4, B. Okay. Let's start doing Gaussian elimination, or also known as row reduction. Let's get rid of that too by adding. I'm intentionally doing a bunch of examples of this because I feel like the only way to really get good at this is just do a lot of examples. So we're going to do row 2. We're going to replace it by the old row 2 minus 2 times row 1. Right. So row 1 stays the same. What does row 2 become? 0, 1, negative 4. What do we do here? We have an A there. We don't know what A is. Well, let's just literally do this, right? I need to do A minus 2 times that 4, right? So A minus 8. So I'm just going to write down A minus 8 there for now. Okay. And the third row looks good as it is, right? That we already have a 0 down here. Okay. Let's continue. So what's the next step? We have a 1 there. Is this in row echelon form yet? It's not, right? Because we have a pivot here. This is the first non-zero entry in this row, the leading non-zero entry. Here's the leading non-zero entry in the second row. But the leading non-zero entry in the third row is not strictly to the right of the leading non-zero entry in the second row. Right? So I need this to be 0 and my non-zero entry to be somewhere over here. Okay. So let's try to turn that negative 1 into a 0. And to do that, we're going to take our old row 3 and subtract off, or I guess we'll just add the second row, right? We'll add 1 copy to the second row. And what happens, we get this. 0, 0, 4 plus negative 4 is also 0. What do we get here? We get A minus 8 plus B. Right. Okay. Well, wait a second. If I can find that page from before. But remember, anytime we get a row that looks like this, the system is inconsistent, right? So we have an inconsistent system here, right? As long as this number here is not 0. So the system is inconsistent if that number right there is not 0. So if 8 is A plus B minus 8 is not equal to 0, okay? Then we just have a contradiction. We don't have any solutions. So we just took care of this case, right? So there are no solutions whenever A plus B is not equal to 8. Exactly. So, so yeah, if a plus b is anything other than 8, this system is unsolvable. Okay. So what if a plus b equals 8? So if a plus b equals 8, then this thing equals 0. So our matrix is 1, 1, 2, 4, 0, 1, minus 4, a minus 8, and then 0, 0, 0, 0. Right? Okay. What can we say about this? Okay. Is this in row echelon form, for example? Yes, it is. We have the 0 row at the bottom. There's my first non-zero entry on that row. There's my first non-zero entry on this row. And this one is strictly to the right of this one. Right? So this is in row echelon form. You just, yeah, I'll say this is in row echelon form. Do we have any free variables? That's always a good question to ask yourself. Are there any free variables here? So here's x1, x2, and x3. Remember, free variables are the columns that have no pivots in them, right? So here, x3 is a free variable, okay? Is a free variable, exclamation mark. What does that mean in terms of the solutions? Well, it means that we can choose x3 to be any number that we want, and we'll get a solution. Right? That's what it means to be a free variable. So there are infinitely many solutions. Great. So that means that there are infinitely many solutions. Whenever a plus b happens to be exactly 8. A plus b happens to be 8, right? Can we ever get one solution? Well, no, because we've exhausted all the possibilities, right? We got a row of all zeros here except for this last entry. If this entry is non-zero, then the system is inconsistent. But if this entry is 0, then we get a column that doesn't have a pivot. And so we have a free variable. So free variables are associated with infinitely many solutions. Let me write that down. That'll be the last thing last point I'll make today. So free variables are associated. This is how you can tell if you have infinitely many solutions. Free variables are associated with infinitely many solutions. As long as, right, as long as the system is not inconsistent. It's just sort of a double negative here, but yeah. So as long as the system is not inconsistent, then whenever we have free variables, we can freely choose them, so we get infinitely many solutions. Okay. So the answer to our question is the system will never have one solution. It's not possible. It will have infinitely many solutions whenever a plus b is 8, and it will have no solutions. It will be inconsistent whenever a plus b is equal to something other than 8. Okay. So hopefully you enjoyed that problem, and next time we'll talk about some interesting applications of linear systems.